Hello, my children. You're watching this in, I don't know, February, maybe March, February, probably February. I'm recording this in December, so you can see Santa Appa behind me. I hope that makes the experience marginally more enjoyable for you. This little Easter egg that's barely an Easter egg because I pointed it out to you directly. Anyway, welcome to Stoichiometry. This is the unit that you've probably heard people complain about, but it's actually fine. Please don't freak out. I know this is a giant word, but it actually comes down to two very simple pieces. If you think about like root words and suffixes and prefixes, this one metry, the suffix metry just means measure. And you know what stoichio means? That's from the Greek for element. We're just going to measure some elements. That's no big deal, right? It's fine. You're going to be fine. Quit freaking out. You're going to be fine. All right. Before we do real stoichiometry, we're going to do a little bit of pre-stoic, which basically is me letting you know the big basic idea here, which is that when you look at a chemical reaction, the coefficient actually tells you how many moles of each chemical are found in the reaction. Did you think moles were going away? That's cute. That's adorable. You're going to be dealing with moles for the rest of the semester. It's fine. You're fine. It's fine. Don't worry about it. The coefficient tells you how many moles of each chemical are found in the reaction. So if we're looking at this reaction, C2H4 plus 3O2 yields 2CO2 plus 2H2O. Looking at this reaction, the coefficients, that's these numbers in front, remember, those tell you not just like that there's 3 oxygen molecules here or 2 carbon dioxide molecules here, but they also tell you there's that many moles of oxygen molecules or that many moles of CO2 molecules. So how many moles of oxygen gas are in this formula? 3 moles of O2. How many moles of carbon dioxide? 2 moles of CO2. How many moles of water? 2 moles of water. You could even just like stick the word moles in there inside the reaction itself, just to remind ourselves that that is a number of moles. And then even how many moles of ethene, C2H4, well, there's no number written in front, but that just means there's 1, baby. 1 mole of ethene. I don't know why I called you baby. That was weird. Let's move past that. How to rock tasty stoichiometry calculations. Stoichiometry is what we're going to do to calculate the amounts of reactants or products needed to make a chemical reaction go. It's basically like using a recipe. If you're given a recipe, you can calculate how much of each ingredient you need to make your food product meal. Like if I'm looking at a recipe for cupcakes and it says it yields 24 cupcakes, then I know that I can expect 24 cupcakes if I follow the recipe. But that also means I might need like 2 eggs and like a stick of butter and, 3 cups of flour or whatever. So if you have all the right proportions of everything, then you can make 24 cupcakes. But if you have too few or too many of something, you might end up with a different amount of cupcakes. So you really got to look at those reactants and products and figure out how they go together, the ingredients and the final meal. So we're going to start with one recipe for a grilled cheese sandwich. 3 slices of cheese, because I'm extra. I got to have some like cheddar and some Gouda and some like Havarti. Yeah. You got to have 3 slices of cheese. You got to mix it up, right? But still 2 slices of bread to make it a sandwich, and that's going to make you 1 grilled cheese sandwich, which is going to be 1C3B2. That's a B. That looks less like a B the more I try to fix it. Let me just erase it and start over. There we go. C3B2, 1 grilled cheese sandwich. In chemistry, we find a ratio of things that we need to make our food. So like I can say for every 1 sandwich I'm trying to make, I need 3 cheese slices. Or I could say it the other way. For every 3 cheese slices I have, I can make 1 sandwich. You could also say that for every 2 bread I have, I can make 1 sandwich. Or you could say it backwards. For every one sandwich I want to make, I need 2 bread. Or you could say if I have 3 cheese, I need 2 bread to make a sandwich. Or you could say if I have 2 bread, I need 3 cheese. So many ratios. Ratios are just a fraction, hun. It's fine. Don't freak out about the word ratio. Come on. There's just a lot of different ways we can compare the reactants to the products or the ingredients to the final sandwich. We're going to use these ratios to calculate the answer to questions like if I have 80 slices of bread, how many grilled cheese sandwiches can I make? Now, I know you can do that in your head probably, but here's the thing, will not be able to always do stoichiometry in your head. So I need you to write the work down so that you can practice writing the work down so that you can like do the work once it stops being about sandwiches. So we're going to write some work down for this. If I have 80 slices of bread, so that's my given, 80 slices of bread. We always start with the given. Remember that? Yeah. And then our unknown is how many grilled cheese sandwiches we can make. So I'm going to start with my given 80 slices of bread. I'm going to multiply times a fraction where that fraction is a conversion factor. Yay. And I need to pick a fraction where the bread is going to cancel out, as they say, where I can get rid of the bread, divide out the bread, and just end with sandwiches instead. So gee, where could I find a conversion factor fraction that has sandwiches on top and bread on bottom? Wait a second, didn't we like literally just do that? Like, this thing right there. So look, one sandwich is made from 2 bread. So the work that I'm going to do down here is saying 1 sandwich and 2 bread. And now I can see a work justification of showing my work to figure out that if I start with 80 pieces of bread, divide by 2 means I can make 40 sandwiches. Again, yeah, I know you could do that in your head, smarty pants. That's not the point. You won't be able to do stoichiometry in your head forever. So you got to show your work. Question 2. If you have 2 slices of cheese, how many slices of bread do you need? Well, it doesn't say 2, it says 6. I can't say words apparently. Anyway, 6 slices of cheese. How many slices of bread do you need? Start with that given, 6 slices of cheese. Your unknown is slices of bread. So we start with the given, multiply times a conversion factor fraction. We need to get rid of the cheese. So what goes up must come down. Slices of bread are our unknown. Unknown always goes on top at the end. What was it? Bread. Unknown always goes on top at the end. So put your bread on top of the end. And then how many do you need? Do we have a conversion factor fraction that compares cheese to bread? Oh, yes, we do. It's right here at the top where we did it earlier. 2 bread needs 3 cheese. So I'm going to do 2 bread and 3 cheese. This is going to end up being, remember, like top times top, divide by the bottom. So 6 times 2 on top is 12, divided by 3 is 4 bread. I need 4 pieces of bread for every 6 slices of cheese. Okay. An easy way to figure out these ratios, rather than just pre-writing all of the ratios and trying to pick the one that you want, that's tedious. Nobody wants to live their life like that, okay? So instead, we're going to draw a little bridge from one food to the next, and that's going to point at whatever numbers should go in our ratio. So for instance, this given on this next problem is 20 sandwiches, and it's asking for slices of bread. So I'm going to start with this given, 20 sandwiches. I know I need to get rid of the sandwiches and turn them into bread. Not literally, because that's a confusing amount of magic, transfiguration right there. We're just going to convert. So I need a number for bread. I need a number for sandwiches. We did pre-write all these ratios, but what if like we're too lazy to pre-write all of the ratios? What if those weren't there because we're lazy, which is fine. We can actually figure out like what bridges the gap from sandwiches to bread? What connects sandwiches and bread? And what connects them are these coefficients up here. So like this 2 for sandwiches, or 2 for bread and this 1 for sandwiches. If I'm starting at the sandwiches, I can draw a little bridge. I call it a bridge. It's a fancy arrow, but I call it a bridge for reasons I'll tell you about in a minute. We're just going to draw a little bridge that says 1 sandwich for every 2 bread. So I can use that 1 sandwich for every 2 bread that's coming from the coefficients in the reaction. And then I can more easily, again, see that we need 40 bread, which again, yeah, I know you could do that in your head. That's not the point. I'm going to be rolling my eyes at an imaginary student. I know, that's the kind of year it's been. Okay. Stoichiometry, we've got this little mole island diagram thing. It's basically sort of a little like reminder that if you're converting between mass and mole or particles and moles, how to do that, what your conversion factors are. But the big key thing here is using your coefficients from the balanced chemical equation to go from moles of a known or given to moles of an unknown. You got to use the coefficients to change moles of one kind of chemical into another kind of chemical. So we have a different reaction now. It's actually the reaction from the top of the previous page, this ethene combustion reaction. And we're going to do some math with this. So this says 8 moles of oxygen gas is our given. How many moles of water is our unknown. And to convert from moles of one chemical to moles of another chemical, we have to do, guess what, stoichiometry, which means we got to use those coefficients in the reaction as our conversion factors. So the easiest way for us to do that without accidentally messing it up is for us to draw a little bridge that always starts at the given, which in this case is the oxygen gas, and it always points at the unknown, which in this case is the water. So in general, I'll make a little note here. The mole bridge always goes from your given to your unknown, okay? Into the unknown, you could say. It goes from your given into the unknown. So your bridge is going to go from your 8 moles of oxygen. That's your given. We're going to need a conversion factor fraction to take our moles of oxygen. What goes up must come down, right? We got to convert it out. So we need to get rid of the moles of oxygen. So we're going to do what goes up must come down. And then we're going to turn it into our unknown. So moles of water go on top because that's our unknown. To get the numbers that go in these blanks, we need to look at the coefficients in the reaction. So we're going to start at our given, which is 3 moles of oxygen right here. Oops. I always draw like a little dot to remind myself that's where I'm starting. Okay, I'm starting at my given. And I'm going to draw into the unknown, into the unknown. Have you seen Frozen 2? I have seen it 4,000 times. So yeah, I'm going to sing the song all unit because if I have to suffer through it, so do you. This is life with a 3-year-old. Anyway, take your little arrow. You're going to start at your given. You're going to point it into the unknown. And those coefficients right there are going to become what you use in your fractions, okay? In your conversion factor. So the mole bridge, this little arrow, always goes from your given into the unknown, okay? That should, if you've drawn your fraction right, that should always be from the bottom to the top of the fraction every single time, okay? If you've drawn your fraction right, that should always be from the bottom to the top of the fraction. It should always be moles of given on the bottom and moles of your unknown on top if you have drawn the fraction correctly. So we're going to take these coefficients and put them into our fraction, okay, from the reaction into the fraction. I like to rhyme and crap because it makes you remember stuff even though you don't want to. Whoops, that was supposed to be yellow. Okay, so from the fraction into the reaction, from your given into the unknown. Some of you are real confused because you haven't been forced to watch Frozen 2 4,000 times, but you're just going to learn like those 3 words of this one song while you watch this chemistry video. Anyway, 8 times 2 is 16 divided by 3 is what, 5.33? That's probably right. I'm not even going to check that because I've done this problem 6 times a year, every year for like 7 years. So I'm pretty sure that's right. If it's not, you can at me or something. I don't care. Okay. This is pretty much what we're doing. We're just converting. So like recap, we were given 8 moles of oxygen gas. So we always start with the given. Okay. We're always going to start with the given. We're still going to have to convert from one thing to another. So instead of converting from like grams to moles like we did in our previous unit, right now we're converting from moles of one chemical to moles of a different chemical, but we're still having to do a conversion, which is why we have a conversion factor fraction right here. In the conversion factor fraction, since the unit is staying the same, moles and moles, the thing that's changing is the chemical. And the only way you can change a chemical is by using the coefficients from the reaction in your fraction. So we said because it was 3 moles of oxygen in the reaction, we're putting 3 moles of oxygen in our fraction. And because it was 2 moles of water in the reaction, we used 2 moles of water in our fraction to convert. So we can do that on this next problem too. If I produce 0.5 moles of CO2, how many moles of C2H4 reacted? Well, we're going to draw the bridge always starting at the given and pointing at the unknown. So in this problem, our given was the CO2 and the unknown is the C2H4. We're always going to start with the given. So that's the 0.5 moles of CO2. I know I'm going to need a conversion factor fraction. I know I'm going to need what goes up must come down to cancel out the moles CO2. I know the unknown always goes on top at the end, so that's the moles of C2H4. Unknown always goes on top at the end. Given is always a what goes up must come down situation. To find the numbers that go here, we used to just always put a 1 in front of the word moles. Back in the before times, which is like 1 block ago for you as you're watching this, back in the before times, we used to just assume we could put a 1 next to the word moles anywhere, everywhere, all the time. You cannot do that anymore because now we're converting moles of one chemical into moles of a different chemical. We are changing something. And the only way I can change carbon dioxide into ethene is if I use this chemical reaction that involves carbon dioxide and ethene. So you gotta like convert. And to do that, we're going to use this little mole bridge where we go from our given, which in this problem is the CO2, into the unknown, into the unknown. Okay, you got to go from your given into the unknown. You got to go from the CO2 into the ethene because that's given into the unknown. And remember in your fraction, if you've written it correctly, given to the unknown should always go from bottom to top also. If you've written your fraction correctly, your given should be on bottom, your unknown should be on top, and you should be going into the unknown. You're going to be so tired of this song by the time we're done, especially because I am like very not Idina Menzel, right? But that's fine. My daughter thinks I'm a good singer, but she has no taste. Okay, 0.5 moles times 1 divided by 2, that's going to come out to 0.25 moles of C2H4. Bam. You just did stoichiometry, or you watched me do stoichiometry. Either one, it's almost the same thing. We're going to move on. We have a little name for this bridge. I kind of hinted at it earlier. We call it the mole bridge. The only or excuse me, the mole bridge is a toll bridge. You have to pay money to get on the bridge, and you have to pay money again to get off because it's a ripoff. The only currency accepted by the mole bridge toll workers is moles. You cannot pay in anything other than moles. They will not let you on or off the bridge if you are trying to pay in something other than moles. If you're trying to pay in grams, no bridge for you. They're going to make you go back to Canada with your grams, okay? We don't, this is America. And because we are like deeply committed as a society to stupidity, we will not be using grams here, even though they make like way more sense than pounds, please. Who needs a base 10 based unit of measure? Take your grams back to Canada. We're going to commit to pounds until our society crashes and burns around us. So you can tell I'm still recording this in 2020 when I say stuff like that, right? Okay. Anyway, take your grams back to Canada. They cannot go across this American mole bridge. Okay. No grams on the bridge. It's moles only. We're going to come back around to that idea when we do a problem with grams, spoiler alert on the next page. But just in general, remember, if you're using that bridge, it is a mole bridge. So you can only have moles in the fraction where you're using that bridge, meaning you can only have moles in the fraction where you are converting using the coefficients from the reaction. Okay. How many moles of iron metal are needed to react completely with 2.45 moles of oxygen gas? We're trying a new problem with a new reaction. And it's going to still work the same way that the previous problem did. You have a given 2.45 moles of oxygen gas. You have an unknown moles of iron metal. You're still going to draw the bridge from the given into the unknown, which in this case, the given is oxygen and the unknown is iron. So we're going to draw our little bridge from oxygen into the unknown of iron. Okay, so that's from your given oxygen 3 to your unknown iron 4, okay? When you actually do your math, always, always, always start with the given. Easy money right there, easy points, just rewrite the thing they already gave you, 2.45 moles of oxygen. You're always gonna have a conversion fraction that you're gonna have to do. And to convert it out, what goes up must come down. And your unknown always goes on top at the end, every single time, okay? When you are converting from one chemical to a different chemical, you can only do this using the mole bridge. You can only do this using those coefficients. The number in your fraction has to come from the reaction, okay? The number in your fraction has to come from the reaction. The number in your fraction has to come from the reaction. The number in your fraction has to come from the reaction. You have never had a more annoying teacher than me. The number in your fraction has to come from the reaction. The number in your fraction has to come from the reaction. The number from, oh crap, I messed it up. Okay, well, it's fine. I probably made my point, right? The given should be on the bottom. You should be going into the unknown on the top if you have drawn your fraction correctly. You should be going from the bottom to the top, given into the unknown on the top if you have made your fraction correctly. So you're going to have that given moles of O2 on the bottom and use that 3 from the reaction. You're going to have your unknown moles of iron on top and use the 4 from the reaction. And this time I'm actually going to use a calculator because I can't do 2.45 times 4 divided by 3 in my head, even if I've done this 6 times a year for the last 7 years. 3.27. There we go. That sounds good. 3.27 moles of iron. Bum, 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 bum. There you go. Y'all, you've done stoichiometry now. And we're going to move on. You're going to have so many more problems you get to try later. But now we're going to add something to it. Guess what? Remember when I said spoiler alert on the next page, we're going to use grams? I'm skipping to the next page. We're doing it now. you have a reaction at the top of this page. It says 4 moles of iron plus 3 moles of oxygen yields 2 moles of iron oxide. Okay, remember those coefficients are always a number of moles. And the problem that we're going to do right now is this gram to mole problem. That is the first one. We're going to save some of this other stuff for a different video. So we're going to go from grams to moles, which is actually number 2. So right now I'm going to skip number 1, but I'm going to do that in a different problem. So like, or in a different video, I mean. So like, don't like completely write it off or cross it out or whatever. So we're going to look at number 2. Is that really what we decided, to do grams to moles first and moles to grams in the second video? That's what we have written down. Okay, that's fine. All right. I would have done it backwards, but I also, who knows really, honestly, I'm just kind of talking to myself. It's fine. Anyway, start with your given, 35.7 grams of iron. You're going to have to convert that. So we need a conversion factor fraction. What goes up must come down. So grams of iron are going to go on the bottom. Here's the thing. We want an unknown of moles of iron oxide, which is a different chemical. The only way I can change iron, Fe, to iron oxide, Fe2O3, is if I use a little bridge. So I need to start with my given iron and go into the unknown for finding moles of iron oxide. Here's the thing, that bridge is a mole bridge. I cannot use that bridge if there are grams involved, because the mole bridge toll workers will throw my grams back in my face and they will say, go back to Canada where things make sense and they use the metric system. This is America and we do things the stupid way. So we're not taking your grams. You cannot get on our bridge. And then you'll never be able to convert anything. So you cannot use a mole bridge where there's grams. This fraction has grams. You cannot use a mole bridge there. It's not allowed. No, it's a big no-no. You cannot do it. They will not accept your grams on the bridge, which means that you're going to need more fractions. You're going to need a whole nother fraction to finish this conversion situation. In general, I will say that if you have a problem where the given and the unknown are both moles, you need, that's a one-step problem, so like one fraction. If you have a problem where the given is grams and the unknown is moles, that's a two-step problem, my friends. You're going to need 2 fractions. So here in this problem, I've got moles for my unknown, but I've got, whoops, I just colored those backwards. I've got moles for my unknown, but I've got grams for my given. That is going to need 3 fractions because I have grams and moles. Or excuse me, I said 3 fractions. It's going to be 2 fractions, 2 steps, because basically we're going to have to convert the grams of iron to moles of iron first, and then with our unknown on top of the end, the moles of iron oxide, then we can use the mole bridge to convert those. Because basically, you cannot use the mole bridge anywhere where there's grams. It's not allowed. So you can't use the mole bridge there. You're going to need a different fraction where you can put the mole bridge from your given into the unknown. So your given of the moles of iron has to go there. Remember, the mole bridge always goes from the given to the unknown, and on a fraction that should be from the bottom to the top of the fraction if you're doing your fractions correctly. So whoops, I just zoomed way out. Okay, so your given moles of iron are on the bottom, your unknown moles of iron oxide are on the top, and this is where you're going to use those coefficients from the reaction. So my given was 4 moles of iron, and then I went into the unknown to 2 moles of iron oxide. Those numbers from the reaction are going to go into this fraction where it's moles and moles, but two different chemicals, moles of one chemical converting to moles of a different chemical. I cannot use that mole bridge on this fraction where there's grams. You cannot give the bridge toll workers grams. They will not take it. You cannot cross the bridge when there are grams. So instead, that's how we knew we needed a whole nother fraction to get a bridge in there and change the chemicals. Meanwhile, you're probably thinking, well, okay, that's great, but like, how am I going to fill in the top of this fraction? I don't know what goes there. Yes, you do. Because you know that what goes up must come down, right? So if we've already figured out from the bridge that moles of iron are on the bottom, that tells me they must have been on top also, because what goes up must come down. So there we go. We got moles, moles, moles. Now, this fraction with moles is kicking it old school, like last block, where you had 1 mole automatically, and then your number of grams comes from the periodic table, which for iron is 55.85. I should probably have that memorized, or at least pulled up. You'd think I would have opened a periodic table before I started recording this video, but you would think wrong. Probably got one in here. Yeah, there's one. I'm pretty sure it's 55. Ah, yeah, it is. It's 55.85. Who knows so much stuff that nobody else bothers to memorize? I do. Okay. Recap. We were given 35.7 grams of iron. We have to convert it to an unknown moles of a whole different chemical, iron oxide. If you are changing chemicals, the only way to do that is using a mole bridge with the coefficients from the reaction going into your fraction. That is the only way that you can change chemicals, is using the moles coefficient in the reaction. That number of moles has to go in your fraction. That is the only way you can change chemicals. So to do this given to unknown changing chemical situation, I had to have a fraction where I first changed the grams into moles, so that then I could use the mole bridge to go from moles of one chemical to moles of another chemical. And when you actually do the math here, which again, remember, this is basically top times top, bottom times bottom, divide 35.7 times 1. You don't need to put in your calculator because you know times 1 doesn't change anything, buddy. Divide by times 2, divide by 55.85, divide by 4. You get 0.32 moles of Fe2O3. And that's a 2-step mole problem. There you go.